Okay, last time we had started to talk about hypothesis testing, specifically hypothesis testing in a situation where you're comparing a sample score with a population score. In most instances, comparing a sample mean with a population mean, but in one instance, comparing a sample proportion with a population proportion. I had indicated that is a three-step process. That is, hypothesis testing is a three-step process. The first step is to define the critical level of the test statistic. The second step is to compute the obtained value or observed value of that test statistic. And then the third step is to compare those two scores, that is to evaluate the null hypothesis. And we're going to explore that in a more detailed way today and across probably the next week and a half. One thing before I go on, I should point out to you, and that is a discrepancy in the text. If you look on page 199 at formula 8.2, you will find it says T obtained equals X bar minus mu divided by S over the square root of n minus 1, which is correct. If you go to the back of the chapter on page 204, you find it there under summary of formulas that it says formula 8.2 for T obtained is X bar minus mu divided by sigma over the square root of n minus 1. That is wrong. It should be S. That is, the denominator should read S over the square root of n minus 1. Okay. Having said that, let's take a look at the four situations that we're going to examine. I'm trying something different. Previously, I have introduced one of the situations, and we've worked through that, and I've provided the formula for the computation of the obtained or observed value, and once we've looked at that, I move to the second situation and repeat the process through the four situations. What I'd like to do instead is to summarize those four situations for you and provide the formulae without working through any problems, and then go to the problems at the back of the chapter and work through those in a way that relies more upon you than upon me. That is, relies upon you identifying which situation you're in and so forth. I think that's more useful in demonstrating to yourself that you can master this material, and will be more useful on the exam. The overall plan is for me to go through these lectures, for you to perhaps go home over the weekend and work through 3 or 4 or 5 of the problems at the back of the text, or back of the chapter. Then I will work through some problems with you on Tuesday and Thursday of next week, and then I will put an assignment of sample problems on WebCT. Let's then look at these four situations. Let me describe these four situations, and 3 of them at least should be very familiar to you. And they should be familiar to you because of our discussions dealing with interval estimation. The first situation is a situation in which you're comparing X bar and mu. N is large and sigma is known. That is, the population standard deviation is known. This corresponds absolutely to the first situation that we examined in the context of interval estimation. In that situation, you rely on a Z statistic. You conduct a Z-test. And the formula for Z observed or Z obtained is X bar minus mu divided by sigma over the square root of n. X bar minus mu divided by sigma over the square root of n. This should be sort of familiar to you, I think, for two reasons. First of all, when we examine this context when dealing with interval estimation, the estimate of mu was X bar plus or minus some Z-score multiplied by the standard deviation of the sampling distribution of sample means, which was sigma over the square root of n. Second, you should recognize this as the general formula for a Z-score, for computing a Z-score. We started, you recall, with Z equals xi, the individual score, minus the mean of that group of scores, divided by S, the standard deviation of the group of scores. Well, now we're not dealing with a sample group of scores. We're dealing with a sampling distribution of sample means. So the individual scores in that sampling distribution of sample means are sample means. And the mean of the sampling distribution is not X bar, it's mu. And the standard deviation of the distribution is not S, it's sigma over the square root of n, which I think is where we were. Yeah. So, when computing the observed or obtained value of Z in context 1, you invoke the formula Z obtained equals X bar minus mu divided by sigma over the square root of n. That is, divided by the standard deviation of the sampling distribution of sample means. The second situation, again, corresponds absolutely to the second situation that we looked at when discussing interval estimation. It is a situation in which you're comparing X bar, the sample mean, with mu, the population mean. N is again large, but sigma, the population standard deviation, is unknown. The formula to compute the obtained or observed value of Z in this instance is once again X bar minus mu, divided by, and I hope this won't be a surprise, S, which is being used to estimate sigma, but because S is a biased estimate, divided by the square root not of n, but of n minus 1. And again, I think that should look familiar to you, because when you go back over interval estimation, what the formula that we used in this situation was the estimate of mu equals X bar plus or minus some Z-score multiplied by S divided by the square root of n minus 1, which is again an estimate of the standard deviation of the sampling distribution of sample means. The third situation, I will go through these three and then I'll take any questions that you have. The third situation is one that has no analogue in interval estimation. It is a situation in which once again you're comparing X bar with mu, but it's a situation in which n is small and sigma is unknown. The critical piece here, of course, is that n is small. In this instance, you conduct not a Z-test, but a T-test, so that you can compute not a Z-score, but a T-score. And the formula for T obtained is exactly the same formula that we invoked in situation 2, and that is x bar minus mu divided by S over the square root of n minus 1. You say, well, why do you use a t-test if you're going to use exactly the same formula? And the answer is that the critical difference in situation 3 is not in the formula to compute the observed value, but as we shall see, in the way that you define the critical value. Okay. The last situation is, again, should again be familiar to you from interval estimation. It's a situation in which you're comparing a sample proportion and a population proportion, and n is large. And here you again conduct a z-test, and the formula for z obtained or z observed is the sample score minus the population score divided by the square root of p subscript u multiplied by 1 minus p subscript u over n, which again should be familiar to you, except in the context of interval estimation, p subscript u, the population proportion, was precisely what we were trying to estimate. So that we had to provide an arbitrary value for p subscript u and consequently for the numerator. And we achieved that by making p subscript u equal to 0.5, 1 minus p subscript u then equal to 0.5, so that if you recall, the numerator was always 0.5 multiplied by 0.5, which was 0.25. But we got to 0.25 start from this formula, which is again the standard deviation of the sampling distribution, this time a sampling distribution of sample proportions. Are there any questions about anything that we've discussed so far? Yes.
The square root symbol goes around pu times 1 minus pu and not pu.
No, it goes around n as well.
All right, thank you.
Yeah. Thanks. Are there any other questions? Yes.
For the proportion formula, will we be able to plug in 0.25 for the denominator to make it a bit easier?
No. No, because in this instance you will know the value of p subscript u. That is, you will be told that, for example, 52% of all voters voted for candidate A. In a particular neighborhood, 55% of voters voted for candidate A. Was there a significant difference between the level of support for candidate A in the neighborhood and in general? There you've got a value of p subscript s, which is 55%, which is 0.55, and for p subscript u, which is 52%, which will be 0.52. So in this instance, because we're not estimating p subscript u, there will be a value for it. Okay? Are there any other questions? Let's then work through an example of this. And let's look at the problems at the back of the text. And take a look at problem 8.2. By the way, the last exam will have a special question on it that will be worth about 48% of your score on the exam. And the question will be, what was the final score between England and Turkey in European qualifying? And the answer is England 2, Turkey 0. Let me say, England 2, Turkey 0. If you can tell me the goal scorers and the half-time score, you get extra points too. No, that's not true. It's not true. It's not true at all. There will be no such question, although if the world were perfectly right, there would be. There is little going on in the world that's anywhere near as important as England's qualifying for the European Championships, no matter what the news tells you. Okay, question 8.2. A student body at St. Algebra College. Healy is a comedian, if nothing else. The student body at St. Algebra College attends an average of 3.3 parties per month. A random sample of 117 sociology majors averages 3.8 parties per month with a standard deviation of 0.53. Are sociology majors significantly different from the student body as a whole? And don't bother looking at the hint. Let's go through this step by step, determine what we know. Do we know X bar? What is X bar? What is the value of X bar? Let me ask you. What is X bar, what is it notation for? No. Let's not now shift our money on the roulette board. And let's also remember that we have to press, hold, and talk. What is X bar notation for?
The mean.
Which mean?
Sample mean.
The sample mean. So what is the value in this instance of the sample mean X bar?
3.8.
3.8. It says a random sample of 117 sociology majors averages 3.8 parties per month. So X bar equals 3.8. Do we know mu?
3.3.
Mu is 3.3. Mu is the population mean, and it says the student body at St. Algebra College attends an average of 3.3 parties per month. That's talking about the entire student body. It's talking about the population. So that mu equals 3.3. We know n, would you agree? It says that a random sample of 117 sociology majors were asked, so forth. It was determined how sociable they were on some scale. Let me ask, do we know S or do we know sigma? Well, the answer is yes. We know one or the other, but my question is really, which one do we know? Do we know the standard deviation of the sample S, or do we know the standard deviation of the population mu?
Sample S.
We know the standard deviation of the sample S. It says a random sample of 117 sociology majors averages 3.8 parties per month with a standard deviation of 0.53. The standard deviation that's given is clearly in reference to the sample. So S equals 0.53. Let's go one step further before I ask you which situation we're in. What is the research hypothesis? What relationship is hypothesized between X bar and...
That they're not equal.
You say that the research hypothesis is that X bar is significantly different from mu. How do you know that? Because it says it in the question. I would agree with you. Where does it say it in the question?
it says, our sociology major is significantly different from the student.
Absolutely. The last sentence says our sociology major is significantly different from the student body as a whole. It doesn't say our sociology major is significantly, do they attend significantly more parties than the student body as a whole. It doesn't say our sociology majors attend significantly fewer parties than the student body as a whole. So the research hypothesis is that X bar will be significantly different from mu, so that the null hypothesis is that X bar will not differ significantly from mu. Would you agree that we know all of these things simply from the scenario? Yes? Let's work through this then. First of all, which situation are you in? Situation 1, 2, 3, or 4?
Situation 2.
There's some support for situation 2. Is any other candidate getting support?
Yeah, 2.
2? How many of you believe it's situation 2? How many of you don't know but presume that I'm going to tell you? It's situation 2. It's a situation in which you're comparing X bar and mu. You're comparing X bar and mu. N is large, that is in excess of 100. And sigma is unknown. What you know is S, the standard deviation of the sample. So we're in situation 2. Step 1 here is to define the critical level of the test statistic Z. To define Z critical. If you recall, on Tuesday I indicated that in order to do that, you need to know 2 pieces of information. You need to know the alpha level, and let's say alpha equals 0.05. And you need to know whether the test is 1 or 2-tailed. From the information you have here, is the test to be 1 or 2-tailed? You say 2? Because? You might want... Because it says so in your notes. That's pretty good.
Because of the null hypothesis is not equal to or not fewer than.
I think you're sort of on the road there. You're on the road to Baghdad, but it isn't everybody. In order to determine whether the test is 1 or 2-tailed, the critical piece of information is the research hypothesis. Would you agree that a research hypothesis that posits that X bar will be significantly different from mu can be satisfied if, first of all, X bar is greater than mu? Yes? But it can also be satisfied if X bar is significantly less than mu. That is, you have to test for the possibility that X bar is greater than mu, that is, you have to test for positive difference, and the possibility that X bar is less than mu, you have to test for negative difference. You have to test both tails of that distribution. Yes? The logic, recall, is this. So we put in the test is 1-tailed. The logic, you recall, is this. And this is going to be micro. This is my micro effort to draw a normal distribution. The logic is this. Here is the center of the distribution, mu. we're going to define some area. An area that, because alpha is equal to 0.05, contains 95% of all scores. And because the test is to be two-tailed, because we have to test both the positive end of the distribution and the negative end, the remaining 5%, that is alpha, is going to be distributed in such a way that half of it is up here and half of it is down here. This is the hunt for Quasimodo and Elephant Man. This is the hunt for Brad Pitt and Denzel Washington and Sean Connery. Yes? We are going to reject the null hypothesis if and only if, when we convert this sample mean into a z-score, it is located in one or other of these shaded areas. So let me ask you, if alpha is 0.05, sorry, the test is two-tailed, I said one-tailed. If alpha is 0.05 and the test is two-tailed, what is the critical value of z?
$1.96.
Would you like to say anything else? Would you like to say plus or minus 1.96 or plus n minus 1.96? I would agree with that. What we discovered when we were doing interval estimation was that what was, among other things, when the confidence level was 95%, that is when alpha was 0.05, you needed to go 1.96 standard deviations above and below the mean to isolate 95% of all of the scores in the distribution. In order to isolate 99% of the scores, we had to go 2.58 standard deviations in both directions. Yes? Yes?
Right.
Thanks. I hope this number 1.96 has taken root, you know, and I'm sure it has. One brain cell up here is holding on to 1.96, and it years from now will come back to you. You'll be sitting at Thanksgiving eating turkey and mashed potatoes, and you'll think, Turkey? England beat Turkey 2-0 in the European qualifying in 2003. And you'll think, where did I learn that? Research methods. That's research methods. And 1.96 will suddenly come into your head, and a tear will come into your eye. You'll smile a little for a moment, but the emotion of it all, a tear will come to your eye. And others at the table will turn to you and ask, is everything okay? You'll wipe that tear away. And again, get stuck into the turkey and mashed potatoes, happy in the thought that England beat Turkey 2-0. So we've defined the critical value of z in this. The second step is straightforward. It's to compute z obtained or z observed. And all we have to do here, they're back. All we have to do here is invoke the correct formula. And the correct formula here is x bar minus mu divided by s over the square root of n minus 1. X bar here is 3.8. So Z equals 3.8 minus mu, which is 3.3, divided by, why didn't you start knocking back? Divided by S, which is 0.53, divided by the square root of n minus 1, which is 117 minus 1, which is 116. Are there any questions as to how we arrived at this point? Yes.
How did you decide that alpha was 0.05? It wasn't in the
I
question.
said so. The researcher decides the level of alpha. On an exam, just as on the exam you were told whether to use a 95 or 99% confidence interval, you'll be told whether to set alpha equal to 0.05 or 0.01.
Okay, thanks.
Okay. Any other questions? If you perform this computation, I think that it's plus 10.16. The third step and last step now is to compare the observed or obtained value with the critical value, and so evaluate the null hypothesis. On this evidence, would you A, reject the null hypothesis, B, fail to reject the null hypothesis, or C, not say a word until Douglas opens his mouth?
Reject.
C. All those who would reject the null hypothesis. Well, show me something. Do something. Show me your hand. All those who would reject the null, all those who would fail to reject the null hypothesis. So we've got about 4 people who would reject the null hypothesis, about 2 people who wouldn't, and about 40 people who are just going to keep their mouths shut and wait till I open mine. I think I'm going to go back here somewhere. I think I'm coming back here somewhere. Let me ask you, if you are 10 standard deviations removed from the average, removed from the norm, are there a lot of you or are there few of you? Let me ask another question. When you look at a sampling distribution of sample means, what is the height of the curve measuring?
The population mean? The population mean?
No.
So the possibility of it landing on the 95%?
No. Let us look at this. My effort to draw a normal distribution here. What does the height of this curve measure? No. I'm going way back. I'm going back to when we first talked about the normal curve. Let me ask this question. In this normal distribution, what is the mode of the distribution? No. Just wake me up when it's over. When the last person leaves after the third exam, will he just tap me on the head lightly, tell me it's over? Good. No. Let's go back. Let's stop talking about, although you eventually get it correct. Let's stop talking about numbers. Give me a symbol. What is the mode of this distribution? What is the mean of the distribution?
3.3.
I asked that we not talk in numbers, but in symbols.
X bar.
No.
Mu.
This is a sampling distribution of sample means. I think I've got up here, although the line has gone in it. Mu. Yeah? The mean is mu. What is the median of this normal curve? Mu. What is the mode of this? Because in a normal distribution, it's like follow the bouncing ball. In a normal distribution, the mean equals the mode equals the median. Yes? The mode indicates the most frequently occurring score. Would you agree? This curve is at its peak, then, at the mode, because that's the score that occurs most frequently. So what does the height of this curve measure? I'll give you, let's play a game, like a Christmas game. I'll give you 2 clues. I'm looking for one word, and the first letter is F. Who said frequency? You win a prize. You get one of those funny Christmas hats. The height of this curve is contingent on the frequency with which the individual scores arrayed along the x-axis occur. So that the more there are of a type of score, well, let's have a type of score here A and a type of score here B. The curve is higher here than here because there are more B scores than A scores. And the peak and the curve is highest here because there are more mu scores than A scores or B scores. So the height of this curve measures the frequency with which scores occur. Would that not indicate to you that there are a lot of scores of this type? There are a lot of scores of this type. There are a few scores of this type. Yes? Most of us are average or around average. Going back, if you don't believe this weekend I'll give you something enjoyable to do. This is assignment 007. Early in the morning, 9:30. You make, and I know that's early for you. For me, it's early in the morning, 4:15. Early in the, but then the other thing is for me late at night, 9:45. Next Saturday, 9:30. You get up, you get in the car, brush your teeth, but you don't have to do anything else. You go down to the closest mall. You go to the food court. You get one of those, you go to that cookie place. You get coffee, half a dozen cookies. 4 of them, those cookies with the M&Ms in, and then 2 chocolate chip and pecan. Because you can't go wrong with chocolate and nuts. And you take with you a notepad and a pen. And you write down 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And everybody that passes, you evaluate their physical attractiveness. That's a 5. You just put a stroke next to the 5. That's a 7. That's a 2. And you stay there all day. You'll probably want to take time outs and go over to McDonald's or the pizza place and get a slice or whatever. At the end of the day, tot up the frequency with which the 1s, 2s, 3s, and so on occurred. Unless you are especially discriminating, they're all ugly, or really not very discriminating at all. I like them all. What you will find is that you have a distribution of this general shape. That most of those folks are you rate in the middle, average. And the closer you are to that average person, the less dissimilar you are from that average person. That is, the more likely one would have to conclude that there's no significant difference between the physical attractiveness of a 6 and of a 5. And that's reflected to some extent with you sitting there going, 5, 6, 5, 6, I guess a 6. You will find very few 10s and very few 1s, very few 9s and very few 2s. And when you do see them, you will react to them as if they are significantly different from the average person. You will either go, oh my God, like Kramer, hideous. Or you will forget about your coffee, your cookies, your notepad and your pen, and you will be following. You know. A friend of mine was in a line where he was checking in at the airport. And the woman behind the counter checked him in and so on and took his baggage. And he turned around to leave. And he had gone about 5 or 6 steps. She ran out from behind the counter, reached him, put her hand on his shoulder and said, I have to tell you, you are the most handsome man I've ever seen. Now, you and I know that if a male says something like this to a female, says, I have to tell you, you're the most beautiful woman I've ever seen, the woman sort of goes, yeah, okay, and sashays off to the plane. A guy told he's the most handsome guy in the world goes, so when are we getting married? They're not married. They're now married. I got to believe she saw him as a 10. I got to believe she saw him as 10 standard deviations removed from the mean. If you are, let's imagine, here's 1.96 standard deviations above the mean. There are only 2.5% of scores above that. How many scores are there above it if you're out in Never Never Land, 10 standard deviations removed from the mean? Surely, if you're 10 standard deviations removed from the mean, first of all, you are a freak. You are a statistical freak. And secondly, and more importantly, you are significantly different from the average. That is, any score that is 10 standard deviations removed from the mean has to be significantly different from mu, the mean of the distribution. You would reject the null hypothesis. You would reject the null hypothesis. And you would conclude that, in fact, on this evidence, sociology majors let me go back. You would conclude there is a significant difference between the number of parties attended by sociology majors and the number of parties attended by students as a whole at St. Algebra College. Are there any questions? Are there any answers? Yes.
So would we reject or fail to reject them?
Ryan, what did I just say? What did I just say in a loud, booming voice? I said if a score is 10 standard deviations removed from the mean, it is significantly different from the mean, from the average, so that one would reject the null hypothesis and conclude that in this instance, at St. Algebra College, sociology majors attend significantly more. No, you would conclude that at St. Algebra College there is a significant difference in the number of parties attended by sociology majors and the number of parties attended by students as a whole. Are there any other questions? Yes. Could you?
Can you clarify what the null hypothesis is?
Can I clarify what the null hypothesis is? Do you mean the null hypothesis in this particular example, or the null hypothesis generally?
Well, I guess when I'm trying to read the book and understand the null hypothesis, so I guess generally.
In its most common form, the null hypothesis is a statement of no difference, no significant difference between the groups. In our example, because the research hypothesis was that X bar will be significantly different from mu, that there is a significant difference, the null hypothesis is simply a statement that X bar equals mu. That should be read as there is no significant difference between X bar and mu. And that's the null hypothesis. Remember when we went through type 1 and type 2 errors? The null hypothesis is the analog to the assumption of innocence in a court of law. That assumption of innocence says that the stream of events, including the defendant, is equal to the stream of events excluding the defendant. That the presence-absence of the defendant makes no difference at all, that the defendant is innocent of any crime. The null hypothesis is simply a statement, in its simplest form, is a statement of no difference. That is, X bar equals mu, or P subscript S equals P subscript U. Is that?
Why does the author go to such? Why is it? Because in saying the type 1 error, the way it's phrased, it's hard to understand because it's incorrectly verifying the null or the. I'm not saying it correct, but it's so many.
If you commit a type 1 error, you make a false conclusion of difference. And if you commit a type 2 error, you commit a false conclusion of no difference. I understand the difficulty associated with coming to grips with that idea because it feels like you're using double negatives and getting twisted around. We're, in a sense, beyond type 1 and type 2 errors now. And to simply focus on the null hypothesis, in its simplest form, the null hypothesis is a statement of no difference. Are there any other questions? Yes.
Like in the previous example, how many standard deviations away from mu would you say if you were going to fail to reject? Because you said 10 is too great of a number. What number would be?
No. Contraire, mon frère. You have, once you've defined the critical level of the test statistic, you have identified the boundary markers beyond which you will reject the null hypothesis. So had we computed z obtained and discovered that it was either less than plus 1.96 or greater than minus 1.96. That is in this open area, the area I'm now shading. We would have failed to reject the null hypothesis. 10.16 standard deviations is way beyond that. Let me say one more thing before we leave today, and that is to point out something in the text. If you recall, when we dealt with interval estimation, I said to you that there were two critical values of z. Yes. So here we have alpha 0.05, 0.01. And here we have the number of tails. 1, 2. You should know already that when the test is two-tailed and alpha is 0.05, the critical value of z is plus and minus 1.96. Likewise, when the test is two-tailed and alpha is 0.01, the critical value of z is plus and minus 2.58. That comes straight out of our discussion of interval estimation. What about these values? Are they standard? And the answer is yes. And if you look on page 193, Healy on table 8.1, Healy gives those values to you. Don't bother looking at alpha equals 0.10 or alpha equals 0.001, but concentrate on alpha equal 0.05 and 0.01. You see the two-tailed values? Either, whether you look at the upper tail or lower tail, under one-tailed value, you see the same absolute score, would you agree? That is, when alpha is 0.05 and the test is one-tailed, the critical value of z is 1.65. And when alpha is 0.01 and the test is one-tailed, the critical value of z is 2.33. If you are testing, if the research hypothesis is that x bar is greater than mu, that is, you're testing for positive difference, these values will be positive. If the research hypothesis is that x bar will be less than mu, that is, you're testing for negative difference, these two values will be negative. And that's all that it means in this table. Where you're testing the upper tail, you're testing for positive difference so that the critical value of z would be plus 1.65 or plus 2.33. Where you're testing the lower tail, you're testing for negative difference, and so the critical value of z would be either minus 1.65 or minus 2.33. This should make it easier. I mean, it's not a matter of memorizing 2 scores, but I think you can memorize 4 scores. You don't have to go to Appendix A and rummage through Appendix A, which would be the alternative. We have now gone through a large part of this chapter in one way or another. My advice to you is, before we next meet, to take a stab at 2 or 3 or 4 of the problems at the end of the chapter. Do not try to do any problem in which n is small. Do not try to do any problem in which n is small, because we have not covered the critical issue in that context, and that is how to define the critical value of t. And you don't do it altogether in the same way as you define the critical level of Z. But my advice to you is to take a stab at a few of the problems at the back of the book that involve large N's. The sooner you convince yourself that you can master this material, the more successful you will be on the third exam. On the second exam, as you know, the questions, in fact, all I did for the computation, for most of the computational questions, was cut and paste from the assignment on WebCT, except I changed the numbers, which should have made no difference at all. But anyway, I think this is the most difficult chapter in the text. I think it's the most complicated. But I think if you, first of all, retain in your head the process, which is invariant, that is, step 1, define the critical value of the test statistic. Step 2, compute the obtained or observed value of the test statistic. And step 3, compare those two scores to evaluate the null hypothesis. And if, second, you start working your way through some of these problems on your own now, I think you'll come to grips with this chapter much more easily than you're likely to anticipate at this point. Are there any questions? I will see you next time then.